Alright guys, the next concept we want to look at is the concept of a unit vector. And the definition of a unit vector is any vector with a magnitude or a length of 1. We talked about the concept of magnitude is pretty much congruent to saying length. So a unit vector, any vector with a magnitude of 1. Some basic unit vectors that we have here, I listed the most basic unit vectors. They are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And obviously if we want to confirm that those have a length of 1, we would use Pythagorean theorem. I'll leave that up to you guys. Hopefully that's a relatively simple process for you at this point. This would be 1, 0, 0, 1 would go straight up, and all of these have a length or a length of 1 here, as you can see as I plotted these points. Negative 1, 0 would look like this. That was not a great line, but you get the picture. And 0, negative 1 would go straight down, all plotted from the origin. These are the most basic unit vectors. Well, what we want to look at is, these are not the only unit vectors that we want to talk about. We want to look at some other unit vectors. So some other unit vectors, you can see I've plotted these down here. Some other unit vectors might look like this. Let me use a different color. This is what we call the unit circle. Alright, the unit circle, we know a circle is going to have a radius that's consistent obviously all the way around the circle. So if this has a unit of 1, then we're going to follow that pattern. Any vector that we draw using that unit circle is going to be what we call a unit vector. So if we look at this, this vector that I've drawn, and I label this vector v, we know a couple things about this vector. We know that the magnitude of vector v is going to be 1 because we plotted it on this unit circle. Alright, so this is, let me just write that down so you have it in your notes. This is the unit circle. And we know that the magnitude of v is going to be equal to 1. Well, let's look at the different components of v. What we can do is chop this into a right triangle. So I can draw a line straight down. And now looking at this, I know that this distance right here is not 1. It's going to be shorter than 1. We'll just call it x. And this distance right here is going to be y. And so I can write this unit vector v in its component form. I know that it travels x units in the x direction and y units in the y direction. Well, this vector is dependent upon the angle that it's going to travel. This looks like it might be a 45, 45, 90 triangle. I'm going to label this alpha here, this thing alpha. And if we know that the magnitude of this thing is 1, what we can do is we can write this this x in terms of those trig functions that we know. So in terms of alpha, I know that this x component here can be written as x over the magnitude of v. Why can I do that? Well, because I know this is a unit vector, and a unit vector has a magnitude of 1, or a hypotenuse in this case of 1. So I can actually write this x component as the cosine of alpha. Why can I do that? Again, because it is the adjacent side compared to the hypotenuse, and therefore the cosine of alpha is going to be an equivalent expression. So similarly, I want to look at the y component of this particular thing. My y component I can write as relative to alpha, it's the opposite over the hypotenuse, or in this case the magnitude. So I can write this as the sine of alpha. So in this particular case, I can actually rewrite my vector v as something that looks like this: the cosine of alpha, comma, the sine of alpha. What this allows us to do, guys, is write our vector in component form here, separating them by components using these trig functions relative to the angle that they make with the x-axis, or relative to the direction. So if I were to draw a different vector, a different unit vector, starts at the origin, and maybe it's a little bit steeper vector here, and it's got a greater angle, well, I can actually figure out what the components are of that vector based on the angle that it makes with the x-axis, or the direction of that vector. I'll show you in a minute how this is a useful tool. One more thing I want to mention here, as if we don't have enough forms, these two unit vectors right here are actually special unit vectors. These are called basis vectors. And they're special because we can actually write any vector in terms of linear combinations of these things. And I'll get to that more in a second. I just want to kind of define this. The basis vector 1, 0, we actually define as I. And the basis vector 0, 1, we define as J. And because these are vectors, we're going to put our little notation up top saying, hey, these are vectors. We know that this vector travels 1 unit in the x direction. This vector travels 1 unit in the y direction. We'll come back to this fact here and relate that to what we were talking about down here. What I want to talk about first, before we do that, is the fact that because we can define these basis vectors, we can now write any vector as a linear combination of basis vectors. All right, and we do that by using scalar multiplication. The general rule is if we have a vector that travels x units in the x direction and y units in the y direction, and we multiply that by a scalar, and think about what that means. Well, what that means is we're going to take that vector and increase the magnitude by what, or decrease for that matter, by whatever our scalar multiple is. What that gives us is a linear combination of the original vector relative to whatever the magnitude is. So we can take a vector, multiply it by some scalar, and what it gives us is it's essentially just a really simple distributive property. The A gets distributed to the x component and the y component, and we end up with a vector in terms of that magnitude times whatever the x component is, and that magnitude times whatever the y component is. So if we want to write each of the following as a linear combination of basis vectors, what we're going to do is split it up into the x component and the y component. So here we know that we know that the scalar is going to be 6, and if I take that 6 and multiply it by what we call I, or this vector 1, 0, that's going to give us the 6, the x component, which happens to be 6 in this particular case. I can do the same thing for the y component of this thing. So I can take my scalar here would be 5. I will multiply it by the basis vector 0, 1. And if I add these two together using that vector addition that we talked about earlier, what it's going to allow me to do is this is going to give me 6, 0 plus 0, 5. And when I simplify that, I combine my x components. That would give me 6 plus 0 in the x and 0 plus 5 in the y, and I'm left with an equivalent expression for my, or an equivalent component form for my vector. So what we ultimately want to be able to do is write this as a basis vector, and we know that these things are defined as, this is I, and this is J. So just kind of a simplified version so we don't have to write this whole thing out. So this thing down here, when we write it as a basis vector, we actually pull that scalar out, and we know that this is 6 times this unit vector, this component vector, basis vector I should say, 6 times this basis vector I, or 1, 0. So I would just write it as 6I. And I add that to 5 times this guy, which we know we defined as j. And this would be the form of 6, 5 written as a linear combination of basis vectors. We can do the same thing over here. A little bit quicker process here. I know that this is going to be negative 2 times I plus, negative minus 1 times basis vector j. So that would be my final answer. So these are really just quick little problems. We really just need to recognize that we want to write these as a linear combination of basis vectors, and so we want this I, j form for these guys. So if we take what we just talked about and writing vectors as linear combinations of basis vectors, and we relate it back to this unit circle that we were dealing with before, we already rewrote this as cosine of alpha, and we know it's cosine of alpha again because it's equal to, relative to our reference angle alpha, it's going to be the adjacent over the hypotenuse, and the magnitude of our hypotenuse is 1, so it would be x over 1. That would be the cosine of alpha. Here's my x over 1, or just x, and same thing for sine. Sine of alpha relates the opposite to the hypotenuse, and therefore we get sine of alpha. So if I want to rewrite this vector v, this unit vector, as a linear combination of basis vectors, I want to rewrite this as a linear combination of basis vectors. What I end up with is vector v is going to be equal to the cosine of alpha is my x component. So I get cosine of alpha times the basis vector in that x direction, which is just going to be I, plus sine of alpha times that particular basis vector, 0, 1. So here's how we write this thing in terms of basis vectors. This one is a little bit easier because we know we're dealing with a unit vector. When you're not dealing with a unit vector, technically what we have to do is multiply that by the magnitude of v, and we'll talk a little bit more about that later. But this is how we write it in terms of basis vector, and this would be our component form up here for the unit vector.